Welcome to the DIY Honda Garage channel. The Diagnostic Trouble Code DTC P1298 indicates a high voltage issue in the ELD or Engine Load Detector circuit within the 2006 to 2011 Honda Civic. This circuit is essential as it monitors the engine load and communicates with the Engine Control Module, ECM, to optimize fuel efficiency and engine performance. If there is an error in this circuit, it can impact the vehicle's electrical system, leading to poor engine operation or diagnostics. A thorough understanding of the components involved is paramount for effective troubleshooting. The ELD is typically located near the fuse box within the vehicle, playing a critical role in ensuring that the engine operates within optimal parameters. The ECM is a central part of the vehicle's management system, coordinating various functions based on input from the ELD and other sensors. The ELD, or Engine Load Detector, serves a pivotal function in your vehicle's performance by assessing the engine load and reporting this data back to the Engine Control Module, ECM. This information is critical for the ECM as it uses it to optimize fuel delivery and timing, which directly affects the vehicle's efficiency and power output. If the ELD circuit has high voltage, it could indicate either a malfunction within the ELD itself or issues in the wiring leading to it. Typically, the ELD is situated near the vehicle's under-dash fuse relay box, making it somewhat accessible for inspection and testing. Any damage or malfunction in this area can lead to a significant impact on performance, creating the need for thorough diagnostics to ascertain the root cause of the high voltage issue. Therefore, understanding the location and role of the ELD and ECM will guide effective troubleshooting efforts. Several factors may contribute to the occurrence of DTC P1298, primarily centered around the ELD circuit. One common issue is high voltage detected within the ELD circuit, which can stem from a faulty ELD or issues with the ECM processing that data incorrectly. Additionally, poor connections or loose terminals at either the ELD or the ECM can disrupt signal transmission, leading to erroneous voltage readings. These poor connections are often due to wear, corrosion, or improper installation in previous repairs, making a visual inspection essential. Furthermore, issues with associated wiring, such as breaks or shorts, can also escalate to high voltage conditions. Identifying these underlying causes is critical for restoring functionality to the ELD circuit and ensuring proper engine performance. The presence of DTC P1298 typically manifests through actionable symptoms, the most notable being the illumination of the check engine light on the dashboard. This alert indicates that the vehicle's onboard diagnostic system has detected an anomaly requiring attention. Additionally, fluctuations in engine performance may become evident, such as lack of power during acceleration or stalling. As the ELD plays a crucial role in calculating engine load, issues within this circuit can also lead to poor fuel efficiency, resulting in increased consumption. Observers may notice unusual smells or sounds as the engine struggles to operate under imbalanced conditions. Recognizing these symptoms early on can significantly aid in diagnosing the specific issue, enhancing the likelihood of a timely and effective repair. The initial step in troubleshooting the DTC P1298 begins with turning the ignition switch to the on-to position, which activates the vehicle's electrical systems and initializes self-diagnostic checks. This is crucial as it allows the Engine Control Module, ECM, to run tests and reveal any existing diagnostic trouble codes like P1298. Before proceeding, it's essential to record all freeze-frame data that the ECM provides, as this data offers invaluable insights into the vehicle's conditions at the point the check engine light was triggered. Additionally, A thorough review of general troubleshooting information specific to the Honda Civic can provide context and guide the technician on potential areas of concern. Attention to this stage is critical to framing the entire troubleshooting process, ensuring that any subsequent actions are informed and targeted. Following the initial inspection, the next step involves checking the Engine Load Detector, ELD, in the data list using a Honda Diagnostic System, HDS, scan tool. This provides real-time data about the current electrical load the ELD is reporting. If the reading indicates 0.2 amperes A or less, it suggests that the ELD is functioning correctly at that moment, allowing you to proceed with further testing. Conversely, if the reading exceeds this threshold, it indicates an intermittent failure, necessitating a more in-depth investigation into potential issues such as poor connections or loose terminals at both the ELD and the ECM. Confirming the ELD's operational status is pivotal to ensure subsequent troubleshooting steps are addressing any underlying causes rather than misdiagnosing the circuit integrity. To continue troubleshooting the ELD circuit, the ignition switch is turned to the lock 0 position, ensuring that the electrical systems are completely off and protecting the technician from potential shocks during testing. Once the ignition is off, the next action is to disconnect the ELD 3P connector, which breaks the connection between the ELD and the vehicle's electrical system. This disconnection is critical as it allows for more direct testing of the ELD circuit without parasitic influence from other components. Preparing for further tests at this stage ensures that the technician can isolate the ELD's performance and allows for accurate voltage readings when the ignition is turned back on. Precise execution of this step sets the foundation for identifying any issues in the ELD's connection or associated wiring. After disconnecting the ELD 3P connector, the ignition switch is once again turned to the on 2 position to provide power to the circuit for testing. At this point, it is essential to measure the voltage between terminal number 1 of the ELD 3P connector and body ground. This measurement determines if the circuit is receiving adequate voltage signals needed for proper operation. If battery voltage is present, the circuit is likely intact, enabling you to continue with further diagnostics. However, if there is no battery voltage, this indicates potential issues such as a blown fuse or breaks in the wiring, requiring additional investigation into the circuit integrity. Such voltage measurements are a crucial step in understanding the electrical health of the ELD system, as they help pinpoint the source of trouble more effectively. In this step, if the voltage measurement indicated no battery voltage, the next logical action is to inspect the number 3 alternator 10A fuse located in the under-dash fuse relay box. The purpose of this check is to ascertain whether the fuse has blown, which would break the circuit and prevent the ELD from functioning properly. If you find that the fuse is intact, it suggests that the issue may lie with the wiring itself, specifically between the number 3 alternator. In this step, if the voltage measurement indicated no battery voltage, the next logical action is to inspect the number 3 alternator 10A fuse located in the under-dash fuse relay box, 3 alternator fuse, and the ELD. In this scenario, you would need to repair any open circuits present in the wiring. Proceeding to step 12 after this checks confirms that you have either restored circuit integrity or identified further issues that need to be rectified before concluding the troubleshooting process. In this 6th troubleshooting step, the ignition switch is turned back to the lock 0 position to ensure the electrical systems are off and safe to work on. Following this precaution, it's necessary to jump the SCS Smart Control System line using the HDS diagnostic tool. This action prepares the system for a more in-depth examination of the electronic components involved in the ELD circuit. Once the SCS line is jumped, the next step is to disconnect the ECM connector A, also known as the 44P connector, which is responsible for transmitting signals between various components of the vehicle. This disconnection is key in isolating potential faults within the ECM, allowing for more accurate continuity tests later. Coordinating these steps effectively facilitates a comprehensive analysis of the ELD circuit, increasing the chances of pinpointing issues efficiently. The seventh step of the troubleshooting procedure involves checking for continuity between terminal number 3 of the ELD 3P connector and terminal A23 of the ECM connector. This continuity test ensures that there is a completed electrical pathway, allowing the ELD to communicate effectively with the ECM. If continuity is present, it indicates that the wiring between these 2 points is intact and capable of carrying signals correctly. Conversely, if there is no continuity, this suggests there is an opening in the wire that needs to be repaired before proceeding further. Establishing continuity is vital in confirming that the circuit can deliver the necessary information for the ECM to respond appropriately. Addressing this issue promptly ensures the system functions smoothly, and you can then advance to the next steps in the troubleshooting process. In this 8th step, the final aspect of troubleshooting the ELD circuit involves checking continuity between the ELD 3P connector terminal number 2 and body ground. Ensuring proper grounding is essential for the ELD to function as intended, as it helps stabilize the voltage readings during operation. If continuity to ground is confirmed, it implies that the ELD circuit has a proper return path, contributing to the overall functionality of the electrical system. However, if continuity is not present, it indicates potential issues such as damaged wiring or poor connections that could be preventing the ELD from receiving necessary signals. Addressing grounding issues promptly will aid in restoring optimal circuit performance. This step is crucial, as inadequate ground can lead to erroneous readings and misdiagnosis in the ELD circuit. Upon completing all necessary repairs following the outlined troubleshooting steps, it's essential to reassemble all components to their original state, ensuring all connectors and terminals are securely fastened. After reassembly, the next step involves clearing any stored diagnostic trouble codes, including P1298, from the vehicle's ECM. This process resets the onboard diagnostic systems, allowing it to run fresh diagnostics without retaining old error data. Following this action, a test drive is critical to confirm that the issues have been addressed effectively and that no new codes appear. Observing the vehicle performance during this drive helps ascertain whether the repairs were successful. By verifying the repairs through these checks, technicians can confidently confirm that the ELD circuit is functioning properly. To minimize the likelihood of encountering DTC P1298 or similar errors in the future, implementing a routine preventive maintenance schedule is crucial. Regular checks of the electrical system components, especially connections and connectors, can catch potential issues before they escalate into significant problems. Ensuring that connections are clean and corrosion-free will help maintain electrical integrity, significantly reducing the chances of high-voltage conditions developing over time. Timely replacement of worn parts can also prevent failures in critical components like the ELD or ECM. Additionally, routine diagnostics can help monitor the system's health, providing insights into any anomalies that may require attention. Proactive maintenance not only preserves vehicle functionality, but can also enhance the overall lifespan of the electrical system. In summary, addressing DTC P1298 involves a nuanced understanding of the ELD circuit and its role within the Honda Civic's electrical system. Troubleshooting this code requires a systematic approach, encompassing everything from verifying voltage levels to checking for continuity in wiring and connections. Each step is fundamental to diagnosing the underlying issues accurately, ensuring the vehicle operates efficiently. Furthermore, emphasizing the importance of thorough diagnostics cannot be overstated, as this process directly influences repair outcomes. Highlighting preventive maintenance measures also plays a key role in preemptively mitigating future issues, reinforcing the need for routine checks. By maintaining awareness of these intricacies, drivers can better understand their vehicles and ensure optimal performance at all times. Please like and subscribe to the channel. See you next time.